We said in week 3, lesson 7, that sometimes information about one event changes our opinion about another event, and sometimes it doesn't. Let's recall the example there. So a number is chosen from our sample set S, which is all the numbers 1 through 12. Let's define A to be the even numbers between 1 and 12. So 2, 4, 6, 8, 10, 12. We'll define B to be the multiples of 3. 3, 6, 9, 12. We'll define C to be all the numbers that are less than or equal to 7. 1, 2, 3, 4, 5, 6, 7. Now let's start computing some probabilities. Probability of A is 6 over 12, so it's 1/2. Probability of A given B, so if we know we're in B and we want an even number, that's 6 and 12, so 2/4, which is 1/2. The probability of A given C is, there's 1, 2, 3 even numbers there out of 7, 3/7. Probability of B is 4 multiples of 3 out of 12 numbers, 1/3. The probability of B given A is, if we know we're in this set, the multiples of 3 are 6 and 12, so 2 out of the 6, 1/3. Probability of B given C is, there's 2 multiples of 3 here, 3 and 6, so 2 out of 7. Probability of C is 7/12. Probability of C given A, there's 3 numbers less than 7 there out of 6, so that's 1/2. The probability of C given B is, there's 2 numbers less than 7 here out of 4, so 2/4 or 1/2. So we can see that knowledge about B did not change our opinion about A. Probability is 1/2, whether we know B or not. So we're going to say A and B are independent. Probability of B didn't change when we knew A, because we got 1/3 and 1/3. But if we compare A and C, our probability of A changed when we knew C. It went from 1/2 to 3/7. Our probability of B changed when we knew C. It went from 1/3 to 2/7. And our probability of C changed when we knew A, and it changed when we knew B. A and C are not independent. And B and C are not either. So the definition is that we call 2 events independent if knowledge of one does not change our opinion of the other. Now, another thing I want you to note is that the probability of AB, which we didn't compute here, so having a number which is a multiple of 2 and a multiple of 3, so basically a multiple of 6, it's 6 and 12, so that's 2 out of 12, which is 1/6. and the probability of A times the probability of B is 1/2 times 1/3, which is also 1/6. So just from this example, it looks like there's some multiplicative property going on here. I'll say more about that in a minute. But first, let's look at the fact, which maybe looks like an accident, that the probability of A did not change when we knew B, and the probability of B did not change when we knew A. So you might wonder if there's always that sort of agreement between the two conditional probabilities, that A doesn't depend on B if and only if B doesn't depend on A, or maybe it's possible for one to depend on the other but the second not to depend on the first. So it turns out that can't happen. If A depends on B, then B depends on A. Let me show you why. So A is independent of B, so given two events, A and B. A is independent of B if and only if B is independent of A. So let's suppose A is independent of B. So that means that the probability of A given B is just the probability of A. Then we can write the multiplication formula. Probability of AB equal to probability of B, probability of A given B, as just probability of B times probability of A. Because we're saying probability of A given B is just probability of A. Now also, the probability of AB could be written as probability of A, probability of B given A. And we want to show that this is just probability of B, but we don't know that yet. But if these are equal and the probability of A is not 0, so probability of AB equals this, and probability of AB also equals that. So since probability of A, probability of B given A equals probability of B, probability of A, then I guess probability of B given A is just probability of B. So B doesn't depend on A either. I guess in this step I'm assuming that probability of A is not 0. Because if we had 0 times 1/2 equals 1/3 times 0, that would be true, but we couldn't cancel the zeros to conclude that 1/2 equals 1/3. So in the claim, I guess I'd better assume events A and B are non-empty or have probability greater than 0. So basically what we're saying is that it's okay to say A and B are independent, not say one is independent of the other, because we have independence one way if and only if we have independence the other way. So we're justified in saying A and B are independent. Now I stated the claim by saying if and only if B is independent of A. So really I should have had two parts to my proof. One that said suppose A is independent of B, and then a second part that said suppose B is independent of A. But actually the second part would be exactly the same because A and B are just two events. We could have switched the A's and the B's everywhere and the argument would have come out exactly the same. So this really is an if and only if claim. Now, an alternate definition of independence is that A and B are independent if the probability of A and B factors as probability of A, probability of B. Well, this is slightly better because there's no danger of canceling zeros or dividing by 0. This is slightly better than saying probability of A given B equals probability of A, because the probability of A given B, probability of AB over probability of B, is defined only when the probability of B is not 0. And this equation is defined even if probability of A is 0. Because if probability of A is 0, then the right-hand side is 0, and the probability of AB would have to be 0, because it's the intersection of A and B. If the probability of B is 0, then the right-hand side is 0, and again the left-hand side is 0. So there's no problem with probabilities being 0 if we use this definition of independence. The probability of both events happening is the product of the probabilities of the events happening separately. All right, let's look at two special cases, then do some examples. If the probability of A is 0, then A is independent of any other event B. And the reason is that probability of AB is going to be 0 if probability of A is 0. Probability of A is 0. So we always get 0 equals 0 times something. Similarly, if the probability of A is 1, then A is independent of any other event B. And the reason is that the probability of AB, so if A has probability 1, and the probability of A and B is just probability of B. And probability of A, probability of B, is 1 times probability of B, which is just probability of B. So the whole sample space is independent of any event, and any empty event is independent of other events also. All right, now for some easy examples. Let's say we choose one card from a deck of cards. let's define events A if the card is an ace. And heart if the card is a heart. So I claim that A and heart are independent. And the proof is that the probability of A and heart is the probability that we get the only card which is both an ace and a heart, the ace of hearts. So that's 1 over 52. And probability of A times probability of B is probability of getting an ace is 1 over 13. And probability of getting a heart is 1 over 4. And that's 1 over 52. So the same thing. Alright, now let's do an example with coin tosses. Let's toss a coin 6 times. And let's define events A, that the number of heads is even, and let's define B, the event that the first toss is a head. And again, I claim that the events A and B are independent. Probability of B is the easiest thing to see here immediately. Probability of B is 1/2. Probability of A is, I guess, the number of ways to get an even number of heads over the number of sequences of 6 tosses. So the bottom is 2 to the 6 because we've got 2 choices, 2 choices, 2 choices 6 times. And how many sequences have an even number of heads? Well, we could have 0 out of the 6 be heads, or we could have 2 out of the 6 be heads, or we could have 4 out of the 6 be heads, or we could have 6 out of the 6 be heads. So that's 1. I'm sorry, I wrote these backwards. 6 choose 0. 6 choose 2. 6 choose 4. I was wondering what the bigger number was doing in the wrong place. One way to choose 0 of them to be heads. 6 choose 2 is 6 times 5 over 2. 30 over 2, 15. 6 choose 4 is the same as 6 choose 2. 6 choose 6 is 1. So 16 over 64. Sorry, 32 over 64. So that's 1/2. Okay, probability of B is 1/2, probability of A is 1/2. Their product is 1/4. Now let's see what the probability of AB is. Probability of AB is the number of sequences. So the first one has to be a head. And then let me say x2, x3, x4, x5, x6 for whatever the other tosses are. So we want an even number of heads. If the first one is heads, I guess we want an odd number in the last 5 tosses. Over 2 to the 6th, the total number of tosses. So h is fixed. So the number of things we're counting are basically, we could have 1 head here in 5 choose 1 ways. We could have 3 heads in 5 choose 3 ways, and 5 heads in 5 choose 5 ways. So that is 5. 5 choose 3 is 10. 5 choose 5 is 1. 2 to the 6 is 64. So that's 16 over 64. 16 and 16 is 32. So 16 is 1/4 of 64. So indeed the probability of AB is 1/4, which equals the probability of A times the probability of B. Alright, now going back to general rules, if we know that A and B are independent, it's natural to ask, does that mean that A complement and B complement are also independent? It does. In fact, it's even better than that. If A and B are independent, then so are A and B complement. And then it follows that A complement and B and A complement and B complement are also independent. So you can take complements in any way you want. If A and B are independent, then all combinations of complementing one or both are independent. So to see this, recall that we always have the probability of A being equal to the probability of A and B plus the probability of A and B complement. Now if A and B are independent, then this is, we can rewrite probability of AB as the product. Probability of A times probability of B. So probability of A equals probability of A times probability of B. We don't know yet that we can factor this, so I'll just copy it. Now if I collect the probability of A's on one side of the equation, I guess we have probability of A minus probability of A, probability of B. That's equal to probability of A, B complement. In other words, now we can factor out a probability of A and get 1 minus probability of B equals probability of A, B complement. And 1 minus probability of B is just probability of probability of B complement. Oh, and that's exactly what we wanted. Probability of A, B complement factors as probability of A, probability of B complement. Now replacing all of the A's and B's, we get that A complement and B are independent. And then since we're allowed to complement any one of the two and get another pair that are independent, we can just complement the B and get that A complement and B complement are independent. The end.